everyone, and welcome to Chemical Reactions Part 1. Now, before we start, let me ask you, if you have a paper plane and you decide to unfold it, will you be able to write on it? I bet you will be able to. But if you burn it, this is not going to be the case. After all, how can you write on ash? It's a new substance formed. If you look at water, for example, I have a cup of water. It is formed of H2O in liquid form. Now, if I put it in the freezer, it will change to a solid. It will freeze. H2O will remain H2O, and you can go back simply by heating the ice, or you can boil the water and recondense it. You're basically changing forms, but composition remains the same H2O. But if you do electrolysis, now this is a different story, because you'll break the water to its elements, hydrogen and oxygen, creating two new elements that were not there before. Now this, my friends, is the difference between chemical and physical changes. In chemical changes, you're making a new product. Like for example, if you're burning wood, you're producing carbon dioxide. If the iron is rusting, hydrated iron 3 chloride is formed. Digesting of food, rotting of plants, these are all new substances. While in physical changes, matter is merely changing form. Water can evaporate and condense. Ice cream can melt, you can freeze it and eat it again. Even if you shred or cut wood, the point is that the composition of the substance will remain the same. And these are the key differences between physical and chemical changes. In physical change, there isn't anything new formed. In chemical change, a new substance is formed. Also, a physical change is mostly reversible. Chemical change, mostly irreversible. Now let us delve deeper in a chemical reaction. What happens basically is that the reactants form the product. But in order for this to happen, the reactants need to collide with each other. And they need to collide with the proper speed and direction for a chemical reaction to happen. But let us consider the rate of the reaction or the speed of the reaction. Do they all happen with the same rate? Do they all happen with the same speed? Absolutely not. Some are very fast. Some are very slow. Consider rusting as very slow. Fireworks, very fast. Now, how can we measure the rate of a reaction? You can do that by measuring the volume of a gas produced against time. Because you're measuring speed, you need to measure time. This is why in all rate experiments, you have to have a stopwatch. Because I'm collecting the gas, I need to have a closed system to avoid the gas escaping. So I need to have a rubber bung or a stopper in my flask. The gas syringe is the most accurate to measure the volume of the gas, but I can also collect the gas and measure it over water. Inverted measuring cylinder in a trough, and the gas will collect over the water. It will push the water down. I'll simply measure the volume every 10, 20, 30 seconds as my experiment goes. The more measurements I take, the better and the more smooth the graph that I will plot. The slope of the graph is the rate of the chemical reaction. And remember, you have to have a closed system for this experiment to work. Another experiment I can do is measure mass loss. Again, let us consider if I have a reaction that produces a gas, and I will put the container with the reactants on balance. I'll measure the initial mass, and by time, gas will escape and the mass will decrease. You plot that and you plot a graph. The slope again is the rate of the reaction. What is missing from the picture? And you know you need a stopwatch. Remember, rate doesn't work except by stopwatch. In this experiment, you notice that I don't have a bung, I have a cotton wool. Why? Because I want the gas to escape. I am measuring mass loss. If I have a stopper, the gas will not escape and the mass will not decrease. But I want the gas to escape and I want the mass to decrease. So I put cotton wool. It will prevent the acid from spraying outside of the flask, and it will allow the gas to pass. Last experiment is if I have a product appearing like a solid. For example, sodium thiosulfate with hydrochloric acid produces yellow sulfur. If I have an X below my reaction flask and I look from the top, by time the X will disappear. So we simply measure the time taken for the X to disappear. And this is how we can measure the rate of reaction, guys. I'll see you in the next video to talk about how is the rate affected by different factors. Thank you.